Good afternoon. So let us start the lesson. So if you remember, the topic was absolute value, continuity, and differentiability. We extensively talked about the absolute value part, but we haven't talked about continuity and differentiability. So let us finish that today. Okay. So the notion of continuity is probably familiar for you. If I say that I have a function which is continuous, I mean if I draw the graph of the function, if I want to draw the graph of the function, technically I can draw it with one pen stroke. Yeah? So that's the meaning of continuity. For example, if I say that, okay, something like this, so that's a continuous function, yes, for example, because I just start and then without lifting my pen on from the whiteboard, I can draw the graph. That's the continuity. So this is a very simple task. If I give you a graph, for example, if I give you this graph and if I give you that graph, immediately you realize there is something, so there is a discontinuity happening in this graph, but there is no discontinuity happening in this graph, yes? So this is a very simple task if you have the graph available. But the point is that we do not have the graph available. We have a function with its formula, and sometimes might be the formula of the function is complicated. We want to understand these kinds of behaviors if this function have some of these discontinuities. Okay? In order to do that, we should formalize this mathematically. How can we define continuity in a plausible way that I can detect these kinds of behaviors having the formula for the function? So because I can define it for you, but I don't want to throw it on you because we want to rediscover it together. That's a plausible definition for continuity that I want to present. So is the question clear? I want to come up with a nice definition of continuity so that if that condition is mathematically met, then I understand that if I go and look at the graph, I will have a continuous graph. Yes? So in order to do that, it is better to consider possible discontinuities and see what is happening in all of them. Try to categorize them to come up with a nice solution for them. For example, one possibility is this. I want to have a strong tool in my hand. Even if the discontinuity occurs at one single point, I want to be able to detect that. Okay, so for example, this is one scenario. I might have one function. By the way, when I draw a curve, I have one single function. Okay? So for example, might be I have this scenario. The graph comes up to some point and then suddenly jumps and then it starts from another point, yes? Something like this. So this is discontinuous. Of course, it is not always discontinuous. It is continuous this part, it is continuous that part. But the whole black curves that you see consists the graph of one single function, but I have a jump here, and that jump is discontinuity. So let us say that this is A. Okay, and there is also another convention here. So, for example, you see in the book, sometimes they put a hollow dot and sometimes they put a filled dot. Yes? This is to emphasize that this one single point is carved out from this part, but this single point is included in the other part. They can do it the other way around. Yes? For example, they can put this filled one, this hollow one. They can put both of them hollow ones, but they cannot put both of them filled ones. Why? Yes?
Because when we write the coordinates, it would have x and then 2y.
2y's, which is against the definition of a function. That's exactly the same thing. When you say I have a function, it means that on any vertical line, either you shouldn't have any intersections at all, or if you want to have an intersection, it should be unique. And that's clear. For example, if I give you this graph, and then, for example, let us say this is 3, and let me go here and say this is 5, and let me go down here and this is minus 5. For example, if I say this is a function, this is of course a big mistake to say this is a function, and that's the reason. If I ask you what is f of 3, what is your answer? It's not clear. Should I answer 5 or should I answer minus 5? And that's why this is not a function. Yes, it is a curve, of course. It's a mathematical structure, but that is not a function. I want you to know, whenever we talk about continuity, differentiability, the main ingredient that I start with is a function. Yes?
What's that called?
Yeah, this is these kind of things are relations. Yeah, so yeah, there is a relation between x and y. The relation here is probably where y squared is x, or plus something. I don't know. Might be. Pardon?
If you have x squared plus y squared equals x, then it's a circle. That's the correct one.
Yeah, but that is not a function.
No, is that just a relation?
That I'm just trying that. So yes, what I'm saying is that you can find a relation between x and y for this curve. Yes, but that relation is not a function. That's the point. So that's why I'm saying that you will not face these kind of things with two filled dots, one on top of the other. Yes, because in that case, you will have the same situation. Another thing that I want you to understand is, let me try to tell you. For example, if this number here is given to be L, and this number here is given to be M, if I ask what is f of a, what is your answer? M. Because if you go vertically up, in principle, this hollow circle dodges you, and then you hit the other one, yes? That's the meaning. So that's M. But if the filled dot is here, not there, okay, then the answer will be L. And if both of them are hollow, what is the answer? It's not defined. It's not in the domain of the function. So these are the alternatives that you need to know about, okay? But I hope that you agree that in any case, this is one possible discontinuity. Okay, yes?
But what if both of them are filled in?
No, I told you, it is not possible. Because if both of them are filled, that will be the same scenario. If I ask you what is f of a, you have two answers, L and M. So this is not going to happen for a function. For a function, by definition, we should avoid this scenario, yes? Okay, so let me now this is one discontinuity. I want to avoid that. Let us investigate why this is happening so that we can avoid this. This is happening, one way of understanding this, that mathematicians have actually did that one. So you are trying to see what is happening when I am close to A. Yes? First, on the left-hand side. So if I ask you, we did this before, if you remember, we had this topic before, but let me just remind you. If I ask you what is the limit of f of x when x goes to A from the left-hand side? If you want to answer that question using this diagram, so it means that you start somewhere close to A, but this negative sign, you remember, it means that I am on the left-hand side of A. Okay, so I am on the left-hand side and I am getting closer and closer to A and try to see what is happening for the height of my graph. So these lengths are getting closer and closer to which number? What? L. Yes? So this becomes L. And I told you before, this symbol, do you remember, means X is very, but this very is a little bit ambiguous, but we have to live with it in this level. So X is very close to A, but X is less than A, strictly less than A. So this is the meaning of this symbol. And so let me write the other way around. In a pair of brackets, I put plus, and then here I say, so it means that if you read the pair of, inside the pair of brackets, you also read inside the pair of brackets. If you read outside all the time. Okay. So this is L, yes? But if I ask you the same question for the right-hand limit, what is the answer? So I will ask this question, limit of f of x, x goes to a plus, and then ask you the same question. So you say that, okay, I stand somewhere close to a, but on the right-hand side, I am not allowed to stand exactly at a. So here, and I try to investigate what is happening to the height of the graph of this function. So for example, I'm here, then I get myself closer to this, and I get closer, and I get closer and closer. So what is your guess about the height of these green lines? They are approaching to which number? M this time, yes? And if I ask you what is f of a itself, what is the answer? In this case, m. Yes? Okay, so I think you realize that something is happening here. These three numbers are not all the same. And then what is the result? You can see it in the picture. If all these three numbers are not the same, I have a problem there. And that problem is discontinuity. Because when I approach to this number from one side, I get one number. When I'm approaching to the same number from the other side, I'm getting a different number. This can only happen if I have a break in my graph. Yes? So this is one scenario. So if I calculate these three numbers and not all of them are the same, I realize that, oh, there is some discontinuity in the graph of the function. Okay? That is the whole thing, yes?
What's the function of such graph?
Yeah, we can talk about that. Yeah. I don't know what the function of this is, but we can think about that. For example, if you go to a post office, so they say that, okay, if your package is up to 1 kilogram, you pay, for example, 10 crowns, but from I don't know, a little bit more than one, it doesn't matter how much, up to 2 kilograms, then you are charged 20 crowns. So if you want to draw the graph of such a function, so the function is that, for example, between 0 and 1 kilogram, I pay 10, but of course, this should be hollow, because that is ridiculous. If I don't send something, they charge me 10 crowns, yes? So this is hollow, it's not in the domain. And then, okay, you say up to 1 kilogram, exactly 1,000 grams, you pay 10, but slightly above 1 kilogram, then you are charged 20. But that is possible, yes? Okay, so I have to put this hollow as well, this one filled, if that's the case. So what does it mean? It means that if my package is somewhere between 0, not 0 of course, up to 1,000 grams, before that, I am charged with this value. But as soon as I reach to 1, then suddenly I am charged, but this is ridiculous, yes? Let us put this one filled, this one hollow. So if you go up to 1,000 grams, 1 kilogram exactly, you are charged 10. But if you are 1,001 gram, then you are charged 20. So you jump up, yes? Yes. And then you go here. So this is also a graph of one function. Okay. But this, if you ask me what is the rule, we can write a rule for it. But that's not a necessity. That's what I'm saying. So we can have one function. If I ask you what is this function, this is the cost function. Yes? So the cost function is consisting of different parts. That's possible. Okay? Okay, so this is one possibility. Another possibility, let us try to check. Let us imagine, what can I have for discontinuity? I can have this scenario. For example, I just want you to imagine what are the possible discontinuities. For example, my function can come here, and then one single point is carved out, and then I go here. Okay? And this function, if I ask you, is this continuous? You would say that, yes, it is continuous everywhere except this one. In principle, can I draw it with one pen stroke? No. Because one single point is carved out. But this is just a little bit mathematical, because one point carved out, you cannot detect it with your eyes, because by definition, one point doesn't have any dimensions. But still, there is one point missing from that graph. Yes? Okay, what is happening here? How can I detect that? Let me give you this number L. Okay, now ask you, just tell me, because we have already studied that before. So if I ask you what is f of x, x goes to a from the left, what's the answer?
L.
It's L. If I ask you what is limit of f of x, x goes to a from the right,
L.
it's L. But if I ask you what is f of a, not defined. Or undefined is better, yes? So undefined. Okay, so that's one scenario. But let me just draw another very similar one. But let me just draw this one. And then exactly on top of that, I put a field dot here. S, and then I give you this is L, and I give you this is M, and I give you this is A. Okay, that's also possible. But still I have this continuity. But let me ask the questions again. So what is the limit of f of x, f x goes to a from the left?
M.
It is M. What is the limit of f of x when x goes to a from the right? M. What is f of a? L. Yes? So you see, I am trying to imagine if I have this continuity, what is going to happen. One thing is clear. This is not the case that all these three numbers are equal. Yes? So here, the limits, the left limit exists, the right limit exists, the function is defined. Two of them are equal, but not three of them. Yes? This is one scenario. And another scenario is this. The left limit exists, the right limit exists, they are also equal, but unfortunately f of a is not defined. That's one scenario. Another scenario is that I have the left limit the same as the right limit. The function also exists at that point, but these numbers are again not all equal. Okay? I don't know, can you have another imagination of breaking the graph so we can check it out? Yes?
I suppose you could make one where it has two hollow points and one filled-in point, but it's like.
That's more, yeah, we can also check that here if you want. I mean, in any case, for example, I can come down here, and then I have a hollow here, and then I go hollow here, and then I have a filled one here or up there, yes? And then, for example, if I say you this is M, this is L, this is P. Okay, now if I ask you what is the limit, and then this point is again as before A. What is the limit of f of x when x goes to A from the left? What is the limit of f of x when x goes to a from the right, and what is f of a itself? So answer these questions. What's the first one? I hope that, yeah, this is M. What is the next one?
P.
It is P, and this one, L. This is even worse, yes? All of them are different. So I mean, in any case, I hope that you agree with me, in any kind that you imagine a break in your graph, even if it is one single point carved out, one thing is clear. This is not the case that all these three numbers are equal. So it means that it is a good way to define continuity. Okay, now can you tell me what is when the graph is continuous at a point? By the way, continuity is not a global property, yes? It's a local property because this graph that you see here is continuous at this point, but completely continuous other points, yes? So that's a local property. Okay, that's what I'm saying. What is the good definition? If you are a mathematician, you want to define the definition for continuity. This is the motivation that you get from your intuition. But then you need to come up with a definition. So let me write it down and I ask you to complete it for me. So I would say definition. So a function f is said to be continuous at x equals to a if, okay, now what is that if? Motivated by this, what can I write? It's on the board. So when do you think I have continuity? I have continuity if none of these cases that you see on the board occurs, yes? Yes, Rasmus, this time?
If the limit from left is equal to the limit, or if.
Yes, yes, yes.
For any point.
Yeah, so I would write the limit from,
Number 8.
so the limit of f of x when x goes to this given number or investigating number from the left, okay?
Is equal to the left and right.
Is it enough?
And it's also equal to the value
Yes.
itself.
Exactly. So actually you see, you are able to define it yourself and it is reasonable. So we say that the function is this one. But if you see it in the book, they have written it in this way. Because if these two are supposed to be equal, these are equal if and only if the limit itself is also equal to that one. So this is why in the book, they have replaced this longer definition with this definition. But of course, sometimes it's good to know it. So what does it mean? If this one single condition, let me just write it for you here. This single condition actually means three things. First of all, limit of f of x, x goes to a, exists. Because if equality sign makes sense, if I am comparing two existing things, yes? So implicitly, this means this limit exists. Number two, a belongs to the domain of the function, or f of a is defined. Number three, these quantities are equal. So when I write that, in principle, I mean all these three simultaneously. But because we are usually lazy, we just write the last one. Yes? Yes, of course, thank you. For example, now you can see that why polynomial functions are continuous everywhere. Yes, for example, let us just talk about one polynomial function. So if I have polynomial function p of x equals to 2x squared plus 5x minus 1. Why this polynomial is continuous everywhere? Yes, why? Because I would say let a be an arbitrary real number, any number that you like. I calculate p of a. What is p of a? P of a is 2a squared plus 5a minus 1. And if I calculate the limit of p of x when x goes to a, it means that I have to calculate the limit of 2x squared plus 5x minus 1, x goes to a. But you know that the limit of this is also the same. It's 2a squared plus 5a minus 1 for any number that you like. So this is why continuous function, if a polynomial function like this is continuous everywhere, independent of which point you are looking at. Yes?
Right, polynomial functions don't include divisions, like or divisions with the variable.
No.
Or not, that is negative powers. So I guess.
Yeah.
So wouldn't you have to first prove that, I guess?
Oh yes, technically speaking, I need to prove why we can calculate this limit in that way. Yeah. Okay. So that's the meaning of continuity. Is that clear? There are some questions in the book, so I want you to also understand them. So let me give you some example. Okay. So let me clean this. That's also good to check something with GeoGebra. Yeah. I give you this function. So usually in your courses, you are used to having one rule for any function. But that is not always the case. Exactly, I just gave you an example from a post office, yes? So you might have different rules for different rules for different inputs. Yes, for example, this is a plausible way of defining function mathematically. So I would say that let f of x be equal to this function, 2x plus 1. If x is greater than or equal to 1, okay? And for example, 2x squared minus 5 if x is less than 1. So that is one single function. But because function means something like this. You have a machine, an operator, you send in some input, you get an output. This is the way that you need to think about functions. Okay, but this function has different functionalities, yes? It means that when I send an input to this function, immediately the function this function does not start the calculation immediately. First, the function realizes what type of input you put in. If the number that you put in is 1 or greater than 1, the function uses this rule to process that input. But if the value that you put into this machine is less than 1, the function uses the second rule to process that data. Yes? It gives you different answers. So be careful, that's the only thing that you need to remember. For example, if I ask you in these kinds of questions, I can have even I can have any number of things that you can see, any number of rules that you want to have, okay? So for example, if I ask you what is f of 2, what is the answer? The input that you are sending in is 2. Which rule I should use? The one above or below? The above. But some mistake I have seen the students, they just put this rule here. So that's wrong, yes? Because if I ask you what is f of 2, you have to replace x with 2. In the normal functions, you have one rule, so just remove that x. But here you have two rules. Which one I should remove? The one above, because 2 satisfies that condition. So it means that when I see these 2, I forget about the second rule. I think that my function is having only this rule. And then I calculate f of 2 using that rule. So this means that I have to replace x with 2. So the answer is 5. And if I ask you, for example, what is f of 0? Which rule the function uses to process? The second one. Because 0 does not satisfy that condition, it satisfies this condition. So when I put 0, I have to replace the x in the second rule by 0. So this becomes 2 times 0 squared minus 5, so the answer is minus 5. Okay? So that's the way that you need to think about this problem. Okay. Now, I will teach you, hopefully GeoGebra will also do this. This is called a piecewise function. Or a function defined piecewisely. I mean, piece by piece we define the function, okay? I hope that in the GeoGebra we have some way to draw these graphs. We will check that one. But before doing that, I want to tell me, do you think this function is discontinuous at some point? Because this is a good question. You don't have the graph in front of your eyes. We want to see that if I draw the whole graph, do I see any discontinuity? The way that you need to analyze the problem is that there is no way this part becomes discontinuous. Why? Because that's a polynomial. Okay? There is no way for this to be discontinuous because that's also a polynomial. But the rule of the polynomial is changing when I go at 1. Might be there, I have two different polynomials. I don't know, might be I have a polynomial like this, and the other one, for example, starts like that. Yes? In that case, I have a discontinuity. Or might be I have a polynomial coming in, and the second one starts from here, takes over from here. In that case, I do not have discontinuity. Yes?
Is there a way to know if it is discontinuous or not?
Yeah, that's the point of the question. Yes? So we want to check this without having the graph. Is that clear? Okay, so by this analysis, you know that there is no point to check other points. If there is something going wrong with this function, it should occur at 1. Because before 1, I have a polynomial. It is continuous everywhere. After 1, I also have the polynomial. It's continuous everywhere. So if there is something wrong going on, we don't know, this should occur exactly at x equals to 1. This is the logic. And then I have to check it. Now my question is that, So this means that I narrow down this question to just one single point. In principle, I have infinitely many points available to check for this function, but by this reasoning, I just narrowed it down to only one single point. For that single point, I have to check it out. How should I check it out? So this is the question. Is this function continuous at x equals to a, at x equals to 1 or not? Yes?
You want to check both of the.
We have to check. We have to check the condition that you mentioned. I have to check the limit of the function. Let me just teach it because I don't want to confuse people. So I want to calculate f of x when x approaches 1 from the left. I want to calculate the limit of the same function when x approaches 1 from the right. I also need to calculate f of 1. Yes, let us start with the simplest one. Okay, can you tell me what is f of 1? For calculating f of 1, which rule is applicable? The above, the one above, or the one below? Above. Because this is accepting 1 from you. This is not accepting it. So what is f of 1? I go to this rule. I replace the x in this rule by 1. So this becomes 2 times 1 plus 1, which is? Yes? And now, if I ask you to calculate this rule, I want you to understand it good. Because you say that, okay, I want to calculate the limit of a function. But this function has 2 rules. Which one I should use? It depends here. When x goes to 1 from the left, it means x is strictly less than 1. So which rule is applicable? The second one. So it means that this function is not obeying this rule. It's obeying this rule. So when I want to calculate in this region, I have to use the second rule. And then if I ask you to calculate it, what's the answer? Don't get confused. This is not minus 1. This is just 1, but on the left side of 1. Okay, so what's the answer? Minus 3, yes? If I put 1 there, it's minus 3. And then you will immediately see that even I don't need to check the next one. Because even if the next one is equal to one of them, it is not the case that all 3 are equal. Yes? But let us, for more practice, let me calculate that. So this is the limit of what? X goes to 1 from the right-hand side. Which rule is applicable here? The first one. Yes? So this is 2x plus 1. And then if I ask you calculate this one, what do you get? You get 3. So this and this are equal, but not all of them. So this means that the function is not continuous. So this function is not continuous. It is continuous everywhere, but not at 1. At x equals to 1. So that is the answer that you have to provide after the calculation. Is that clear? Okay, let me see. I have some idea, hopefully, how it works in GeoGebra, but let us check that one as well. I think we need to use some kind of if, like a programming things, but I think it will work, yes. Because I already checked that. Yes, it works. So let me just delete it and start. I want to put this function here. So you write f of x. It's good to learn this one as well. And then you put equal. But there is no one single rule. So I have to use if instruction. Yes, I would say that if, and then if it is as usual, GeoGebra gives you the correct syntax. So I will not use this one, condition then. I will use condition then else. Yes? So because I would say if this is the case, this one, else the other one. Yes, that's the meaning. So I use this one, and then the condition. So what is the condition? For example, let me put this in. Okay? X is greater than or equal to 1. So let me just use the keyboard here. So I use this one, if, condition, then else. For the condition, I type in x x is greater than or equal to 1. Okay, and then comma. So can you tell me what should I write for then here? This reads if x is greater than or equal to 1, then the function is 2x plus 1. Am I right? Okay, and then I go to else. Else what? Else means that if x is not greater than or equal to 1, it means that if x is less than 1, it should be 2x squared minus 5, yes? So it becomes 2x to the power of 2 minus 5. Am I right? Yes? And this is your graph, by the way. And so it was detected that it is not continuous. So this is the way that you plot. This is called a piecewise function. So you see that the left-hand side is a parabola, by the way. Could you expect that? So let me, by the way, draw this line. The line x equals to 1. Let me also draw this black line. This black line is not included in the graph. I just drew it because I want you to understand what is going on. The left-hand side of this black line is, if you see, is here, which is a parabola. Parabola with a minimum, because this is positive. And the right-hand side, you expect this should be a line, yes? And that's exactly what's happening on the GeoGebra. And then you also see discontinuity here, yes? So we have a jump here, yes?
Can we see like fill those fill on the
No, and that is reasonable, because how can you say GeoGebra to carve out exactly one single point? Yes, but the way that I did it in my figures, I drew a circle with a very small radius, and I filled it and I make it hollow. It is possible. So I just use this as an object. If you want to draw a graph for teaching someone, you can generate it, but you cannot expect that GeoGebra can carve out one single point.
Can they put those circles in?
Yeah,
I mean,
I put them by hand. So I drew the graph, and then I made a very small circle and just connect it to the end of that one. This will work. Okay, but now question, it's a programming question. I'm just curious, how can we put 3 conditions here, by the way? Because GeoGebra does not provide that, did it? Because when I put it, so let me just go back here. So for example, you want to check this function. F of x, let us just try to write something. It is 2x squared plus x minus 1. Say x is less than 1. And then try, I don't know, is it possible using GeoGebra? It should be possible combining ifs, yes? So for example, I would say a square root of x plus 1. Let us make life harder for GeoGebra, okay? So x plus 1, and then x goes up to 2. And then this one x including, this one excluding. I'm just randomly writing something. And then, for example, I have x to the power of 3 minus 3x squared plus 1 if x is greater than or equal to 2. How do you think we can put this in GeoGebra?
just put an if inside the else place. I don't know how they will render it, but
So let us just do that. I think it's good. I mean, so let us start with some ideas. So I will go to GeoGebra here. That's a fun practice. You can also like it, I think. So I will write g of x because I have already written f of x. Don't get confused. So I will start with if part. So what did you say, Rasmus? So we choose this one.
yeah.
Okay. And the condition I put from the beginning. So let me write x is less than. I don't know where this keyboard went.
You can just write if you want.
Okay, anyway, x is less than 1. Then you say that I put 2x to the power of 2. Yes, and then plus x minus 1. Okay, and there is no one else. You are saying that I put another if instead of else.
Yeah.
It seems reasonable. So I start with another if. Okay, and then I have to fill it up. Okay, so fill it up. So again, what do you expect to put there? Your condition.
Yeah.
Your condition is 1. I don't know where is this keyboard.
You can just write less than
And then equal. Okay, so I will do that. You mean this? Okay, good. It worked. And then x, and then less than 2. Yes. And then the rule is oh, square root of, so what should I do then? Where is this keyboard?
Just write square root.
Yeah, I don't want,
SQRT.
yes, I will do that. SQRT, and then x plus 1. Yes, it worked. And then I go outside and then put a comma and then write again the other one. This means else. Yes? So so x to the power of 3, and then I go down minus 3x squared, and then plus 1. Yes, I hope that we haven't done anything. Are you ready? Yes, it worked. So this is also possible. So you can put if inside an if, and it will generate this one. By the way, what is the graph? That is the graph. So let me just take this off. This is your graph. And how many discontinuities you see here?
2.
So I have one jump here exactly occurring at 1. Another jump I see at 2. So the function is continuous everywhere except exactly these 2 points. Is that clear for everyone? So you see, let me just change this to a pen. So here, you see this is a jump here, and there's another jump here. The function has broken into 2 parts exactly these things. By the way, let me ask you a tricky question. Do you think this is part of a straight line? The middle one? Is it or not? This one looks like a line segment. Do you agree with me? Is it a line segment or not? Definitely. Yes or no?
No.
No, why not?
It's from the square root.
Yes, it's a square root, yes, because that's the middle one. The middle one is the square root of x plus 1. This cannot be a line, yes? It is not a line. So if you want, you can draw the complete picture here. So y is equal, now square root is back, x plus 1. So that is your graph. So this is the red one, is square root of x plus 1, but I was only interested in the graph where it is between 1 and 2. So this is why you just saw that part. Okay, so that's also good to know that GeoGebra is also capable of doing things. And if you want a better challenge, make it 4 and try to put if inside if to see if it works, okay? Anyway, now the lesson of continuity is finished. There is one part which is actually very important, and that is the lesson of differentiability. Of course, we already talked about differentiability, but we want to talk about this at the level of graph of a function. Okay? So, do you remember what was differentiability? That was exactly what I started with. I would say that if I give you a function, and if I give you a point A in the domain of the function, belonging to the domain, then you calculate this limit. This is a limit. Sometimes a limit exists, sometimes it does not exist. Yes? If it turns out that this limit exists, you say f is differentiable at a. And the value of this limit is called the derivative of f at a, and is denoted by f prime of a. Okay, this question is harder. I am asking you, because do you remember? I ask you what is your opinion about if the function is not continuous. You could imagine some cases, and then we come up with a definition for that. But if I give you a graph of a function, how do you know that the function is differentiable or not? By looking at the graph. By the way, let me just review. What is the geometrical interpretation of this number? It is the slope of the tangent to the graph at the point whose x-coordinate is a. So that is, you have something in mind geometrically. So it means that if I give you a graph, for example, if I draw this parabola, is it differentiable everywhere? Yes, because the derivative is what? 2x, and 2x exists everywhere. This is one way of doing it. And if you draw the graph of this parabola, this is a nice curve, smooth and nice. Okay? But now can you imagine if I want to face a problem and the function is not differentiable, what type of things you should expect in the graph. Yes, Simon?
And maybe that the point is undefined.
No, okay, that is, I will actually rule it out, because when I want to start, I assume that it is in the function. So this is, in that case, it is not defined. Of course, it is clear that the function is not defined. But that is not, I would say, about that. Yes, another type of points. By looking at the graph of the function, if you want to detect the points that the function is not differentiable, what type of properties you expect? Intuitively, you need to connect it with the notion of tangent line. If the tangent line exists at that point, the function is differentiable at that point, yes?
Yes, if
For example,
like you said, if you have one point that's not connected to the other graph.
So discontinuity, you have the name now. You don't need to, you just call it. So if I ask you to draw a tangent line here, it doesn't make sense. Yes, you can't draw half a tangent line, but a tangent line means something goes forever from both directions. That's the meaning of line. So, yes, you are right. It means that if I am facing a discontinuity, I cannot draw the tangent line in a plausible way. But of course, if I want to prove it rigorously, you have to wait for the university. It's not hard theorem, but this is something that we can prove. Okay, but is this the only scenario? Yes, you are right. So one type of points that the function is not differentiable are the points at which the function is not continuous. That is one category of points you need to remember. But can you imagine other type of points? Yes, Rasmus?
Where you have like I guess that the derivative would be decision is the best way to describe it. Basically, like when the
No, I give you the pen. Let me make the problem simple. I want you to draw a curve for me so that it is not discontinuous, because we already learned about discontinuity. Now I want you to draw another graph and show me that at this point of the graph we do not have differentiability.
would be that the graph looks sharp at some point.
Sharp.
That
Exactly. That's a good word that you use. For example, if I come here and then go back like this. Okay? Is this function, by the way, continuous? It is continuous but not differentiable at this point, because the notion of tangent doesn't make sense at the sharp point. If I give you the pen and the ruler and I ask you to draw a tangent line, you probably don't say anything to me, but you can laugh at me because you say that Babak is crazy. How can I draw a tangent line to this one, yes? Exactly, if you ask a person in a round room, go and say that, okay, go and sit down in that corner. Okay, which corner then it is? Yes, that's exactly the same scenario. So you want to actually put a tangent line, there is no tangent line going on. I have a half a tangent line, by the way, don't get confused. I can draw a half a tangent line here, but that is, yes, that is reasonable. It's called half a tangent. But if I continue, then I will mess up. This is not tangent, yes? So that is why sharp points, we have to exclude them. These two are in your book. The points that Boyle mentioned, so whenever a function is discontinuous at a point, be sure the function cannot be differentiable there. And there is another point of sharp points, even though the function is continuous, it is still not differentiable at that sharp point. There is another kind of points that the book hasn't talked about. Do you have questions?
Yes.
Yes,
What
please.
is the difference between half a tangent line and an array?
That's a ray. There is no difference. I mean, another word for it is a ray. But of course, this is the tangent ray. Yes, because it is a ray and a tangent, so I called it half a tangent line. But that's exactly the same. Now, can you imagine other points? I think it's not hard, but I don't know, for some reason the book doesn't talk about that. Yes?
Function of a vertical line. The case value is
Exactly. So, but can you imagine such a graph or not? So he's saying that. So this is another type. The function is continuous. The tangent exists, but it is still not differentiable because it happens that the tangent is vertical. Okay, and this can happen. I cannot draw it perfectly. I can draw it by GeoGebra, this function. For example, if you draw the graph of this function, the graph of this function is like this, similar to this. It goes tangent in that way, and it goes like this from that way. So the y-axis is tangent to the line. By the way, do you remember what is the name of this point? We will come back to that later. Inflection point, because the concavity of the function is changing from that passage. But anyway, this is the game. By the way, you could understand it analytically. Why this is not differentiable at 0? Let us calculate. I calculate the derivative. How should I calculate the derivative? Do you remember? X to the power of 1/3. And if I ask you what is the derivative, 1/3 goes down. X to the power of 1 unit less, it is -2/3. Let me write it with positive powers. So this becomes the 3rd root of x squared. So this is my derivative. This is my derivative. Now, if I ask you what is f prime of 0, what is your answer?
Undefined.
Undefined, yes? That's exactly the same thing. This is predicted here. Yes, because if I ask you what is f prime of 0, it means I am looking for the slope of the tangent line at the point x equals to 0. On the other hand, we know this is the case. If I put 0 here, it's undefined. Is that clear? By the way, we can also confirm that I have done it right. So if I want to put the 3rd root in GeoGebra, there should also be a way. So let me get rid of all these. Yes, and then I would write, probably I have to go to the functions. Yes, here. I use that one. So let me type y equals to this one, and I put 3 on top, and then I go, oops. Where is this equality? And then I go here, x. But that's the graph. So you see, as we predicted, the graph is like this. Okay, and then probably, yes, we can actually make it a little bit nicer so you can see that. That's the graph. Yes? So that's the graph of a 3rd root of x. But this is excluded in your book. So if I want to summarize, if you want to look for this non-differentiable points, you need to look for discontinuous points. You need to look for sharp points. And if you want to know something more, you need to look for the points at which the tangent line is vertical. These are only 3 points that the function cannot be differentiable at that point. Is that clear? Okay. But let me solve this problem. I want you to do this graphically. This is the last problem I want to talk today. They called this is a level 2 problem, but I mean this is. Let me just summarize that. I want to ask your opinion. So I would write continuity implies differentiability. Differentiability implies continuity. Yes, and then I would say discontinuity implies non-differentiability. Okay, let us confuse you. And then the other way around, I'm confused myself now. So what is the other alternative? Can you write it down? I should have 4, yes? Continuity, differentiability, differentiability, continuity. Okay, non-differentiability. We don't say we say discontinuity, yes. So I want to ask your opinion about the truth or falsity or falsehood of this. Discontinuity. Okay, so I will take blue and red. Okay, this one is true or false? If I give you a function which is continuous at a point, is it guaranteed that the function is also differentiable at that point?
No.
Why not?
Because you have a vertical.
Because of one of them is vertical and the other one is sharp points. So this is false. Yes? Okay, differentiability implies continuity.
Or you mean locally or globally?
No, I'm talking about locally, yes, because differentiability is also at a point, continuity is also at a point. I'm talking about it to be honest, I have to say if the function is continuous at a point A, is it differentiable at a point A? But I'm just suppressing those things, yes. So do you think differentiability implies continuity?
True.
So if it's on a single point, is that considered continuous?
Yeah. Because for
No, because if it is not continuous, we just learned what happens. It's not differentiable.
Yeah.
Yes? I am telling you, differentiability implies continuity. If you say no, it means you were able to find a point which is differentiable and not continuous. But this cannot happen. So this is true. By the way, it's an important theorem. I didn't prove them rigorously for you. I relied on your intuitions only. But there is a rigorous proof for that. If a function is continuous at A, then it is also, if it is differentiable at A, it is also continuous at A. Okay, what about this one? Discontinuity implies non-differentiability. That's exactly the same thing, written in a slightly different language, yes? So that is also true. What about the last one? Non-differentiability implies discontinuity.
False.
If a function is not differentiable,
It doesn't mean it's necessarily that it's not.
yes, why?
Because
Again, the sharp points, yes? So that is also false. Yes?
You wrote non-differentiability wrong.
Okay, yes, thank you. Non-differentiability, thank you. Okay, so this is good. So you learned whatever you are supposed to learn. And then one example, I want to solve this from the book, but the problem is that it is problem 2242, part B. So 2242. It's part B, it's page 74. So next time I will continue with the next chapter. This was a little bit hard, so I wanted to do it later. So the function is given, y is equal to two rules. X squared, x is less than or equal to 0. Am I right? Yes. And x if x is greater than 0. The question is that, do you think this function is differentiable at the origin? Okay? I don't know how the solution is. I don't know if they expect you to solve it really correctly or they want to rely on your intuition using graphs. Okay? So let us do it the simple way. So, can you draw the graph of this function, by the way, without GeoGebra? It's extremely simple. Because either it's a parabola, the famous parabola, or it's a line, depending on which direction I am, on which side I am, yes? So, you can say that, okay, the graph of this one is this parabola, yes? But here, I am not interested on this part, because I am interested for this when x is negative. So I clean this part. Do you agree? So something like this. Of course, I was a little bit careless. It is tangent here. Something like this. So I had this in my memory. I cleaned that part which is for the positive part. And this one, I also have it in my memory. This is the angle bisector here, yes? So this is the angle bisector. But for this one, I am interested on the positive x part. So I clean this one. And then I have this one. Yes? So this is the graph. So it comes like this, and then goes like that. Okay, do you think that this function is differentiable at the origin? No. Because it's a sharp point. You can also confirm that yourself using GeoGebra. I think this is simple. But I don't think it is hard if we really want to do it mathematically rigorous. Let us do that. It could be fun, okay? So I don't know, because if it was level 3 problem, I would definitely assume that the one that I want to do right now is the solution. But because this is a level 2 problem, we still. So if you don't mind, instead of y, let me write f of x. Okay, the question is this. Is this function differentiable or not? Okay, I have to calculate, is it differentiable at 0 or not? So I have to see if this exists or not. So what is the definition of limit? The limit of f of a is 0 in this case, minus f of a divided by h goes to 0. Now that is the problem here, you see, because I have two roots. Okay, can you tell me how to fill them up? What is f of 0 by seeing the picture? Or by seeing the rule, of course? 0, because 0 is acceptable by this part, and 0 to power 2 is 0. So that is 0. But that is the problem. Because this is f of h, and then how many rules I am facing? 2 rules. I don't know, because you know that do you remember when we wanted to calculate the derivative using the definition? You had one single rule, so you just put that rule there. But here you have 2 rules. Which one I have to choose?
Remove the above.
So why do you say the above one, not the other one?
No, because it's limited, you can't really.
Yeah, so this means that I have to break the limit to 2 parts. Yes, because when h goes to 0, it means that I am very close to 0, but it is not clear I am on the positive side or on the negative side. And unfortunately, it matters. Because if I am on the positive side, this is the rule. If I am on the negative side, this is the rule. So this motivates me, in order to answer this question mark, I'm motivated to break the limit to one side and the other side. So I calculate this once, and I calculate this second time. And then I compare the results. If these results are the same, the right and the left limits are the same, so the question mark is the same number. If the limits are not the same, this limit does not exist and the function is not differentiable. Do you expect which one? Based on your intuition. Do you think that the numbers are supposed to be equal? No, because we know that I have a sharp point, so the function shouldn't be differentiable. Okay, so let us check. How can I calculate this limit? H is h goes to 0 from the right hand side. So h is a slightly positive. I'm on the right hand side. When it is a slightly positive, this is my rule. So what is f of h? F of h is h itself. Yes? And the answer to this limit is just simply 1. For this one, h goes to 0 from the left hand side. H goes to 0 from the left hand side. So f of h should follow this rule. So this becomes h squared over h goes to 0 from the left. This h and this h are cancelled, so this becomes the limit of h goes to 0 from the left, so the answer this time is 0. And because these two limits are not equal, so this means that does not exist. So f is not differentiable at the origin. So this is a completely rigorous way of doing it. And by the way, Could you predict that the left limit is going to be 0 without calculation by looking at the graph? Why? Because the left limit is the slope of the half left tangent. Yes? So if I ask you what is half left tangent, it's this line. And what is its slope? Is 0. And the right limit is the slope of the half right tangent. But this is just a straight line. So the tangent is itself is equal to itself, and you know the slope of this line is 1. Okay? So this is the meaning of the sharp point. If you want to have a definition for a sharp point, it means that the half tangent line on the left and the half tangent line on the right, they make an angle which is not 0 or which is 180. So that is something, that's the meaning of the sharp point mathematically. Okay, any questions? No? So this part is finished, and the next lesson I will go back to chapter 4, okay? So we continue with the properties of the graphs of functions. Thank you.